All right, so first, I guess we'll start with welcome to the Physics Monastery. Echelon and I formed this, and now we're taking on volunteers as a project to try to change the world. And I mean that as literally as I can. We have a project that we believe is going to help not just transform the sort of technology we have access to, but transframe the way we conceive what we're accessing. Right? So whenever you transframe, you're also changing what you think you are. So the world becomes something different as we evolve, psychotechnology evolves, right? As we take on different concepts that allow us to access the world to different degrees of freedom, different levels of accuracy, right? So what I want to do is start with a bit of the story. Of course, we could tell the story for hundreds of very delightful hours. Almost every giant discovery in the history of humanity waking up throughout all cultures, all of them have contributed in very big ways, right? But the big story that I want to really, I'm going to cherry pick some ideas along the way, of course, because I have to tell a subset. But the ones I want to cherry pick are the ones that help most cohere with the story we now tell in physics about what reality is. Okay, so we'll have to eventually get to that story also, but I'm going to try to build up some of the insights we've got that changed how we thought of the world. So we need to first then catapult ourselves back, if we can, in our minds, to what it must have been like to conceive the world around us before we had all the modern technologies, before we had the modern tools by which we just are used to or accustomed to now interpreting the world, okay? But there's a lot to say into that, but let's try to imagine that you're before a literate world, okay? Before people write things down in any way, before they abstractly write anything down. The limitations of that world are what compared to what we're used to now? What's the advantage literacy gives you over not having literacy in your mind? What else can you do? Or what can't you do compared to what we're used to doing now if you're not literate?
Communicate ideas.
You can talk, right? But you can't abstract the things you're talking about. And because you don't have any way to practice abstraction, you're stuck. So it's hard to make any progress that way. So one main reason is because the way we think is we're mapping the world. We're trying to tell story inside. And by inside, I mean the big realization for consciousness is that we are ontologically blind, right? That means we're actually completely blind. And what we think we're seeing when we have our eyes open is what our brains have learned to interpret from the inputs coming in. But it's just our interpretation that's making what we see as the projection. So if we want to investigate the world in a way that's checking against the projection we're making up about it, and we have to first become aware that the story we're making up is being made up by us. That's a huge step. So we didn't get to that step right away. To get to these paths, we first needed to figure out which things were important to navigate with. What you're seeing is a set of available affordances. You're seeing there's a place for me to sit. You're seeing this is a thing that I could pick up or grab. You're seeing the ways you could engage with your reality, and your brain is making up the story of those things because you've practiced engaging with those things, right? So the elements of reality that you have no practice engaging with, something that you've never yet seen or grasped, you've never conformed your comprehension to, you own no eidos of that form. You don't have any way to map it inside of you and therefore understand it. So the goal through history seems to be growingly clear that over time the goal is really to give each individual intelligent being an access to more insights, because insights are something we all find inherently natural. What do I mean by that? We're in a point in history right now where all of us find some things absolutely natural and normal that were completely impossible and never heard of once 1,000 years ago, right? Now, are we all geniuses compared to everyone 1,000 years ago? Absolutely not. Very arguably, all worse. we don't manage, we don't engage with the world in a way that's as rich and necessary as they used to. So you could very easily argue we're dumbed down compared to them. But why is it we're all able to understand these things they didn't understand? Because we were given the insight. Insights are a reframing, a different story. If someone can give you a story that makes sense of something, then you go, ah. You don't go, no, I don't like that. You go, ah, I can see better, right? So the story developing is what we're really after. And the best development process we have for story formation at this point is, I would argue, science. Right? Science is our process for trying to tell this story, for peering into reality and finding out which parts are real. That's a difficult question. Everything you engage with, how would you find out what's more real and less real? Which patterns are really there? Okay, it's surprising perhaps to imagine the clues that you can just see from looking up, but in the astronomical world, in astronomy, a lot of our history of mathematics fell out of observations from looking up into the stars. Okay, literally, right? And what do I mean by this? How far should we go back? When we look at the world, right, the first position or framing we might take of it is that we're at the center, and the further out away from us has a different sort of quality in the sense that it belongs to this world, but the world's still extended from you, and the sky moves around it, right? So this was the natural picture we all knew in our history, the flat earth world, or even if you had a round earth world, you still imagined the sky was the thing that was going around you. What was the sky made out of? Stars that are what? What was the story back then? What are stars?
Gods.
Gods, yeah. So inexplicable things. Well, not all the stars were gods, actually. The planets were gods. Why? Because they wandered. So most of the stars, they might not be explicable in the sense that you don't know why they are there to begin with, but they keep a certain pattern and they just go around and around and around. And you watch that a few times growing up, and that part seems a little, well, I can predict it's going to do it again next time. Easy to predict, right? But then there's a few stars in there, if you watch real carefully and get to know the patterns. Some stars don't stay with the rest of the stars. They move around. And it's not so easy actually to come up with a way to predict why or where. Okay, they do go pretty much linear over time as they move through, but sometimes they do these weird loops and then go back. Okay, so this really mystified people. Think about this. You're looking into reality by finding a new way to look, by focusing on the stars, the structure around you, and trying to interpret what's going on. And some of the stars seem to have wills, right? Now, how much of a will? You can argue all kinds of stories, but seems to need a story that gives them something special, okay? So we need to explain motion now of the heavens, right, in order to stand our reality, or it becomes a feature of our reality that needs to be explained. Okay, there's a basic start. A big step was when a big step was the start of the birthplace of science, which for our Western tradition started basically at Anaximander, who realized that if he takes a stick and uses it as a ruler, meaning set it as a base length, I'm going to call it equal to 1 meter, whatever unit you make up, but the stick is now one stick, right? But it's a special stick. And he could use this stick to do something that would resolve reality more accurately than anyone had before. Now, this is something that maybe is magical to realize the first time, if it is the first time you realize it, but since we are just imagining the reality we see, we need to find a way to check the story. And if we're just checking by looking into what we're already imagining, that's not really checking. He found a way to check. Okay, now, obviously he wasn't the first person in history to measure things. He was the first person in the Western culture to come up with this concept that you could standardize a measurement and therefore understand something more accurately. For example, if you've lived somewhere and you've always stood on a hill, you think it's particularly beautiful, and someone comes up and argues with you, well, how far away do you think the peak of that hill is, your favorite spot from right here at your house, right? Well, you might want to know, but you might have an answer already from your projection. Oh, that's exactly 1 mile, right? You have an idea. You see it from your point of view as 1 mile. And then you can say, well, let's go check. And now you can take the stick and actually go measure. And you can get not just the first digit, but you can get many digits depending on how accurately you measure, right? So the big key is that measurement becomes the birth concept of science. If you can figure out how to measure something, you can figure out how to explain it in more detail than your brain is currently making it up, which means if you can then understand the story behind that new detail, you can start to see it. You can start to see reality differently, right? That starts to be the goal over time. With this insight, Alexander also instantaneously comes up with this need for inventing maps, which is kind of a big deal, and the early invention called a gnome for like a sundial. So basically, it's just a stick that's standing up and has a shadow, and the shadow goes around. But the shadow goes around in a very predictable pattern. It's not exactly circled, first of all, right? Because it's going to be at an angle, but it's angle subtended. You can mark it off and make a time calendar out of this, and it'll come back around the next day and start. Technically, if you've done it, I've done it a few times, over the seasons, the shape changes. But still, then it will repeat. Okay, so you can use this sundial just by putting a stick in the ground, and then for the next year, marking off specific times and increments, and then you now have a way, you have the whole path through the year to then mark off time, right? You have a way to measure time. That's a really big deal. Now, compared to the way we measure time today, it might not seem impressive, but the concept of measuring time, to use that sort of way to more accurately engage with reality and see if what we're thinking is right or wrong, and then hopefully update if it's wrong, right? That is a very important step. We have better resolution now, thankfully, but we're gonna see where that resolution's gone. The main point is that the step for the birth of science comes with this notion of measurement, right? If it's science, it's something to do with something we're measuring. What's the advantage of this? What does this do for us? It means we get to use numbers, right? And numbers we trust because numbers are where the five senses can converge. But that's another way of saying that measurements are measurements of kinds. What can you measure? It turns out that every type of measurement you can make, every dimension that describes the type of measurement, not the number, but the dimensions, can be decomposed down into only 5 kinds. This is an enormous insight that took a long time to get to, right? But what are those 5 kinds? Alexander came up with measuring 2 of them right up from the bat. So time, and then space, right? Measuring time, measuring space. Now, right away, you should let all your uncomfortable feelings about, well, what is time and space kind of resurface, right? Now, not that we're saying there isn't anything that is time or there isn't anything that is space. It's that when you're measuring it and it's the base, it's the dimension of measurement, we really need to be comfortable with what we mean by that base. What is time? What is space? Now, through the most of history, we have no idea, right? We start to learn new aspects of their relationship. We start to learn new aspects that we can tap into and use them for, but still they become the base of our description in science because science stays the measurement way of looking richer into the world. Now, let me focus on that point a little bit. If we made a really good circle, way better than this, but use a computer to make a really good circle, okay? And then you came up, or you asked any human with really good eyes and good dexterity to then, you give them a measuring tape, and they need to measure the circumference and the diameter. Yes, they already know the ratio, but I want them to measure it themselves. I want to see the accuracy with which they get to actually parse the world, okay? Well, when they're done, they're going to get a ratio. They're going to get the circumference over the diameter, and it's going to be approximately equal to pi. How approximate? How accurate? How many digits do you think they're going to get? Do you think they could get to 2 just with their naked eye, with their hands and eyes?
With just your naked eyes, no measuring?
No, using the measurement.
Oh, using a measurement.
But you have to still identify it with your eyes. You have to look at the hash marks and say, this is the number.
I would say you can probably get to 3.1 or maybe 3.4.
Yeah, maybe there, maybe, right? But you're not going to get to here.
No.
Nobody is going to, right? Now, can we engage with the world more accurately than that? Yeah, of course we can. We can get tools that do it, but our eyes need help past this. To see better than that, you have to have the story right. I should say it that way, huh? To see better, you need to theoretically know what's going on. You need to believe in this number we call pi, which we then can calculate the rest of the digits of. You need to geometrically expect it to be that. So science then becomes, at least the modern version of science, it took a lot of starts of ideas and so on to become a global conversation. But now I think a good way to think of science is as the conversation about what reality is. Okay? It's the conversation about how to look into it new ways, how to interpret the data we've got from looking into it new ways already, right? It's that conversation. And it's a completely open conversation still. It's not settled. Now, we've certainly figured a lot out. We've gotten to a lot more precision of clarity of picture, but we have a modern picture that's not settled yet. I mean, nobody in physics would say we're done. Okay? Why? The short answer is because we have two competing models of our description. We have quantum mechanics and we have general relativity. And they exist as accurate descriptions of what we see in the world on different scales. But they're not compatible, they're not incommensurable. You can't mix them. They don't say the same things on their mutual scales. So if we pick a small scale and apply the rules of general relativity, it doesn't map to quantum mechanics. And if you pick a big scale and apply the rules of quantum mechanics, it doesn't map to general relativity. So there's something off. It can't be both. It must probably, most people assume, there's a deeper, richer theory underneath both of them, connecting them. Okay? That's the modern position of where we're kind of at. But since science is the game of figuring out reality, we have to collect facts about reality to figure it out better, right? The arguing about it part is an important part, but only if we're arguing about the better facts. Here's a new fact, here's a better measurement. We've looked further into this number and now know this, for example. Well, in order to do that, you have to turn it into numbers. You have to turn it into a fact. You have to make a measurement, right? Great. So, if we're making measurements, what are the other basic kinds of measurements that are available? Out of all the complex things we can measure, like something's redness, something's temperature, list every property that we know exists. If it's a property, then it should be a thing that should have a measurable essence to it, right? Otherwise, you can't really call it a property. So what other fundamental essence could there be? Which ones? Do you guys remember? Do you have a guess?
Quantities.
Quantities? Okay, that's a number of amount, but not of kind, because it universally applies to all of them. So good, that's a good point to have. But if we just restrict to just kinds, then time and space might suggest mass, good, and charge, and temperature. Good. Now, where the five senses converge, or where the five bases converge, are numbers, right? You can make a measurement of something's temperature and give it a number. We can measure a mass, give it a number, charge, space, and time. But when you're taking a measurement of something and giving it a number, don't you need to preset the unit scale of the measurement? Right? How big's your ruler? That needs to somehow be said, right? There's going to be a confusion that's going to take a lot of brain power to kind of stare at and see what the resolution is here. There's bases, we call them the dimensions, time, space, charge, mass, and temperature. But what's the scale that's appropriately assigned to time? What's the scale appropriately assigned to space and charge and mass and temperature? And if you give me one, how could you possibly justify it? Right? I mean, there does seem to me to be a natural scale I would naively expect for time. If I say, what's the smallest possible amount of time? I would say 0. That's the limit, can't have less than 0. So if the answer is not 0, I find it absolutely baffling, or I need an explanation, right?
Otherwise, it's arbitrary.
Yeah, same with the rest. So the problem is also then you need in relation to something. If I tell you I'm going to make my base unit 1 for time, 1 what's? 1, we'll call it seconds. But if I haven't defined what seconds are, it's a unit. You need your seconds to somehow have some coherent meaning And how could it possibly be coherent and have meaning if there's no other measurement? It must have coherent meaning in reference to the other possible measurements. Kind of following? Okay, so we have, in order for science to be able to look deeper into reality, it's got to take measurements. So that's the game of science, is to figure out how to make measurements, right? So at first step is to figure out how to isolate your environment so you can tweak one parameter at a time and then measure what it does, right? Try to find out how to only change one thing at a time and then infer what's happening from the measurement, or get new data about what's happening and then try to interpret it. But if we're going to make sense of all 5 dimensions at once, I think this is the big open question in physics, is what are the dimensions at the base to begin with, right? We're assigning numbers and things to these things, and we're finding relationships between these things. But if you don't think that temperature, mass, charge, space, and temperature even exist or persist in reference to each other, all of them become entirely arbitrary. How much of this is clear? How much is not? It's all clear?
That's all fair.
Okay. Okay, so traditionally, before the insights that we're making with this model, with manifolds, the minimum manifold actually, the argument for why seconds versus hours for the base of time and so on is something that's widely, it's not completely, there are people who understand this, but it's not something that's mainstream caught on to yet. The connection between these bases is defining the absolute limit of things we can measure. Follow me? So science is the domain of measurement, right? It's all the possible new ways you can come up with, cleverly measuring something to look into it further, but only by measuring. And if you can only measure 5 bases in total, now it can be complexly put together, right? You can have 5 of these and 12 of these and 4 of these, or put a denominator or whatever, right? It can be built up with many of them. But if we only have 5 possible measurements, kinds of measurements to make, then it implies that there is a base projection or base class of persistent form. Yes? Why? Because each one of these bases has to get defined in reference to the other bases. It can't, everything else would be arbitrary. The other bases in the same actions, in the same system that you're creating or maintaining. Okay. So another big step, of course, is ontological depth perception, which was invented by Thales, the first philosopher, natural philosopher, right? So what is ontology? Anybody have a good definition for ontology?
It's a worldview, how you view the world at all. How do you interpret your measurement?
Yeah, the study of nature of being, right? What things are. Ontological analysis, when you're using reasoning to try to get at the underlying structure of reality. So if you're trying to peer further in by making sense of the measurements you made, right, then you're doing ontological depth perception. You're trying to try on a different story and take on a story that reframes the world. So that's, I think, what you were getting at, right? Your ontological perspective then frames your world. And we've all got, maybe, I mean, if you're getting older, you might have less and less experience with it. But as a child, we always reframed, right? We get new information and we reframe. We grow up. There's no, of course, reason we need to stop doing that when we get a job, but apparently that's what we do. Yeah, this reframing process is now given basically all over in the hands of the philosophers or people making measurements, the scientists, right? Okay. How far have we reframed? Our current story is now in the form of Dirac, meaning there's an equation called the Dirac equation that's made up of 5 parts added together and equal 0. So all 5 parts added together equal 0, and those 5 parts connect. They have a column matrix made of 4 pieces, and each one has the same 4 pieces, but they rearrange their positions. So it's basically a transcript for how you take 5 things and mix them up in a perfect Mobius construction way. Okay, so the transform on the Dirac equation going from right to left would start you from a state that mixes and ends up in a state that's exactly the same in that they all started negative, then they all end up negative. But if they were 1, 2, 3, 4, then they're going to end up 4, 3, 2, 1, exact opposite order. So this is a transform between 5 things that does the thing you want in a Mobius connection. You end up exactly like you started in one way, but exactly opposite in the other way. Then if you take that state and put it back in the beginning, do it all again, you end up exactly where you started from the very beginning. So it's a two-state transform, or mod 2 transform. Yeah, okay, great. But that equation captures the symmetries in the transform, but it doesn't tell us what scale it's supposed to be happening at. It doesn't tell us how these things connect. Follow me? It tells us that they have symmetries they must share if they are connected, but it doesn't tell us the picture of what it looks like. What scale are things breaking up and twisting around? It doesn't give us that information. It gives us the basic structure of a spinor. To go further, we need to figure out what these things actually are. Right? We need to know what time and space and charge, mass and temperature represent. We know their dimensions, we believe that they're real. In fact, we might believe that they are the most real things. But we don't have a very coherent story for them yet. And that's, of course, what we're after. All right. Let me give another measurement example. Galileo came along, and apparently, at least according to the records we have, was the first person we know of that decided when he saw things falling that he wanted to measure how, right? That's kind of a big thing. So everyone had looked into reality to the point where they'd seen things fall, they'd dropped things, they'd gotten familiar intuition with gravity. But it wasn't until Galileo came along that anyone thought to actually measure how things fall under the influence of gravity. And how do you do that? Do you need to be a super genius to do this?
Drop stuff.
Yeah, you need to be able to measure time. You need to be able to measure space. So until someone's thought of that, you can't measure gravity, but you need to measure those, and then you just need to go make the measurements, right? Drop something and see how much time it takes. Now, you could do it straight down. You could drop something this high and see how long it takes to hit the bottom and, measure how much time it takes. And then go higher and drop it, right? That's one way, and this time, so it took more time. You can keep doing this and get your measurements this way, right? So now what are you measuring? In gravity. You're measuring a relationship between space and time captured in gravity somehow. You're looking into gravity about its own space and time relationships. Genius, really, but until it's thought of, it's easy once thought of, I guess, because you could all go now do this. Everyone in their own homes can go make these measurements, right? And if you want to make it even easier, because we have stopwatches that are way more accurate than his, so you can do this. You can outperform him very easily, especially if you spend a little bit of money to get some, sensing devices that touch and so on. You don't have to use your fingers and your timing. But still, you could also take a slope, right? You could take a ball and roll the ball down the slope. You can make the incline different and measure how much longer it takes. You can measure all kinds of things about how gravity is pulling things down, okay? And you already know how to go do that, right? You might not expect what the answer would be. You have no prediction of what to expect. Well, when I try that, what will I get this time? But you can go look. So here's a cool insight. You don't need to know what to expect to go look this way, right? To go measure. The Dirac equation is the symmetry exchange that exists on boundaries we call the Planck constants. And there's a Planck time. There's a Planck length. There's the Planck charge. The Planck mass. I like to take the time to do this because I wanted to kind of sink in. And the Planck temperature. And we're going to give these symbols because we want to talk about them quite in detail, because unless you understand these, you can't understand these. So the Planck time is the symbol like this, and all of them are going to be kind of the same way. We're just going to put a sub P. Charge is Q, mass is M, and temperature is capital T to distinguish it from time, which is lowercase t. Okay? So what are these? Well, these are the mysterious limits of the 5 dimensions connected by the Dirac equation that show up because of the Dirac equation. Now, they don't show up as in their predicted, the Dirac equation predicts a symmetry exchange. And what scale it happens on, no idea. When we look in the real world, we go measure the constants of nature. We measure the speed of light, we measure the Planck's constant and gravitational constant, measure magnetic constant and the electric constant and so on. There's all these constants that describe fixed character in nature, right? We measure these constants and we apply them to the Dirac equation. And when we do, how do I say this? These constants applied to the Dirac equation give us these boundaries. So whenever we try to symmetry exchange, try to assume where can we close the symmetries with these constants, where can we take the dimensions they're measuring of and cancel them out. For example, cancel out so that there's only one Planck time left or one Planck length left. Any constants of nature you can do to sort them together so you cancel down to just one time expression, cut down to there, it'll be the Planck time. So these boundaries are somehow in these constants, but these constants are complete mysteries. The boundaries we imply for these constants give us the actual boundaries to apply the Dirac equation on, right? But the explanation for why it's there is still missing. So that's where we're kind of at today. We have a symmetry exchange that gives us everything in quantum mechanics, 44 scaling parameters that belong to it, right? So this is the explanations plus the symmetries of the actual structure of reality we have right now for the electron and all of the happenings of quantum mechanics. Okay, so here we get to a little socio-political situation of the modern current times. So this quest to make sense of reality, which I consider the central aim of science, the whole point of making measurements is so that you can correct how you're conceiving and therefore seeing reality and correct how you engage with it therefore, right? If you don't see stuff that are always there, you're not going to engage with them. Who's likely to be the most qualified people in the world to work on this problem still? The theory of everything, the explanation for the symmetries we find in reality and the concepts of nature and so on. Would be, first guess, physicists,
Yeah.
mathematicians. The strangest things have happened in academia ever since business took over the world. What do I mean? You might imagine if you were a physicist and you wanted to go into physics, you would learn about this quest to uncover the picture of the world, right? You would learn about all the little cool things about electrons and protons and neutrons. You'd put together all the different forces. You'd get a story in your head, and then you would think, now I'm finishing my degree and I'm going to continue working on this story. But you're not allowed to. That's a bit of an extreme thing. You're allowed to in some small, subtle ways, but not the direct ways. You cannot get funding, cannot, anywhere in the world, and people complain about this all the time in the undercurrents. You know, people who are willing to speak up despite might losing their jobs for speaking up. We're not looking for the explanations for these, despite the fact that our story of reality right now is that it is composed of these symmetries with these boundaries maintained under the symmetry exchange of the Dirac equation. Okay? We need a story there. We need an explanation there. So, strangely, physicists aren't looking because they can't get paid to look for that. And mathematicians aren't looking. That's weird. Why would that be? Mathematicians have been put in this weird, awkward position socially now, where in order to be a mathematician taken seriously, you can't apply your skills to the natural domain. You're not a natural philosopher, you're a mathematician. What's the thing that distinguishes a natural philosopher or a physicist from a mathematician? A mathematician doesn't concern themselves with the natural domain. Now, why would someone have invented a club that takes the people who have the best skills, math, and tell them, as long as you're in the club, though, you can't work on this? So, fortunate for us now, all the people in the world who could be working on this problem aren't, so it's up to us. Okay, so we have clues. We have lots of clues. Why? Because we're in the domain of measurement. We can make sense of things if we've made measurements. We have somewhere to start. And the biggest step is we don't want to get stuck in our storytelling. You might go off a wrong path, but then you can check. You can always make a claim, and now you know what to check against. But if you can't get any claims, you get no starts of an idea, you're really just spinning your wheels. So I want to get us past that. That's the first big thing. And here's the first step to doing that. When you have no idea what the answer is, say I'm going to throw you into an imaginary classroom. If you have to take a test and you've never been prepared for the subject at all, you have no idea what's going on, but you get to choose between an essay question test and a multiple choice question test. Which one do you want? Multiple choice for sure. If you really know what's going on, you probably want the essay one because you want to really explain it well instead of just marking a circle, not so satisfying. But if you have no idea, you would rather have a possible option in front of you that could be the answer than no idea, right? Good. So if we can change the game we're playing here, instead of from being a game that the next step is someone please conjure up the answer, change it to a multiple choice. Someone please find an answer that fits. Find all the answers that fit, and then we'll see which one's best, right? This is what we want to do. But how do we do that? How do we do that with the constants of nature? Well, we have to look at the measurements they represent. We have to look at the data they represent. So this one, 2.99792,458 meters per second. I should have to put times 10 to the 8 meters per second. Let's do this piece by piece. This is the content of a string of digits, a power, a scaling, and a relationship between two fundamental dimensions of length and time, right? Okay, that's what this constant is telling us. That's the only thing it has. It has a number, a power, and a relationship between length and time. So somehow this number has to tell us something about the relationship between these two, right? That's what we want. We want to get somewhere where it makes some sense of it. Okay, same thing with all these constants. They have a string of digits. They usually have some error, but this one we cut off right here, and we basically normalize everything to it. When we're doing the comparisons between constants and stuff, this is one of the ones we really like, so we're going to normalize to it. So we assume it's 0,00000 for the rest of the digits. But what this really means is we're only explaining the world out to this accuracy for now. Okay? All right, so thing to keep in focus is that when we have a measurement, in each case, we have a string of digits, that's one kind of information. We have a power, it's another kind of information. And we have the kind of dimensional relationship that these two things are relating to us to begin with. Okay. To make it clear how the Planck constants come from these, how we get from the constants of nature measurements to the Planck constants, point out that the speed of light is the Planck length divided by the Planck time. Okay? So it's a fundamental restriction built into the relationships of the things you can measure. Whatever, we're trying to get at what these dimensions actually are, but we know what they are is the things we're able to measure. But why are we able to measure those things? Why are they of this kind? Why do they have all the properties they have built into them, right? Why do they build this structured world of order of very interesting structure all the way up to quaternion order, right? Why does that come from these mysterious 5 dimensions? Okay. So if we have all 44 of these constants written out in numeric form with their power, write them all in base 10 times, so in what we call a scientific notation, we write a decimal after the first digit right there, and then how many digits do you have to move the decimal to get to the actual number is 8. Okay, but we want to write them all so that we have just one digit up front so we can compare them in some interesting ways and then compare the scales independently if we want. Okay, so this is scientific notation. We're going to write them all like that so we can compare them in a uniform way. We can try to look for patterns in these measurements. Why? Because we know these measurements aren't just random strings of digits. These measurements are somehow telling us something about the relationships that the dimensions of the stage of reality maintain, right? And we want to peer into those relationships so that we can see that stage, so we can understand what's really going on. Okay. first step is that when we list them all out, we would try to keep track of what dimensions each one is, right? And the first thing you can check is, well, I should point out, when you use this method to use these constants to solve for these 5 Planck constants, you can only get numbers that are accurate to like 5, this one goes to 9, but the rest are about 5 significant digits. Then there's error, a lot of disagreement between the constants in what that limit is now. Follow me? So they all agree fantastically at first, in scale, in number, and everything, but then somehow you can't get this one and this one to come together to make exactly the same number as if you use this one and, for example. Okay, so there's some piecewise construction going on, and one of them's way bigger than the other. But at some point, the other one starts to play a role that throws that number off, because now we have another contributor in the geometry and the balance in the construction. Okay, so that means we're going to need some sort of balance where we have a first part and we have some second part. And we want the second part to be much, much smaller in scale than the first part. Okay? All right, that's a good step. Now let me try to give a little historical speed up, because we could play this game for a very long time. It's quite enjoyable, but we're not going to make any conclusion from any single thing we pull out. Well, we could, but what we want to do is we want to play the same game for every constant of nature, and find the algebraic expression in terms of the Planck constants, in terms of the boundaries of the dimensions, so that we can see how those boundaries actually fit together. And if you can get 44 bits of information about how the boundaries are fit together, there's 44 intersections where something's connecting, right, where there's some balance happening, then you have a much higher resolution of the form you're talking about. So that's our strategy. Follow so far?
You
Right.
didn't explain why 44.
No, I didn't. It's just that there are 44. When we go measure, we look into the world and go get them, and there's 44. But let's give a little explanation. If there's 5 dimensions, 1, 2, 3, 4, 5, and we wanted to do 5 factorial, what does that equal to? 5 times 4 times 3 times 2 times 1, which is 120. If instead we put this exclamation point on the other side of the 5, it's now, instead of being a factorial, it's what's called a derangement, which we'll get to in a bit. But it's a slightly different function, but related to the factorial function. Now, we end up getting 44. Okay, so give me a bit to get there. But for now, if you have 5 dimensions, and this is being very vague because we're not specifying what the dimensions really even are, but if you have 5 things of any kind, and you want to know how many ways can they be deranged, the answer is 44. Okay? So if you have a system made up of 5 things, let's pick these kinds, these 5 things, then those 5 things should have 44 different ways they arrange in sequence. Okay? So, interestingly, we have 44 constants of nature. 44 expressions from the 5 base dimensions that are making the expressions. Okay. If we keep going through all the constants, this is the way I did it. It took me a while to come to the insight that we needed to be breaking things up into the big piece and the small piece. Okay, so I'm going to put that in the future of the conversation for now. Pretend we don't know that yet. To try to get an answer for each one of these numbers, we want to get an answer that what? An answer that we can make some sense of, right? So say you have no idea what the answer might be, but you know what the question is. Those are the forms of questions we now have access to if we use the tool like Wolfram Alpha, right? So we put in this number into Wolfram Alpha. We can set it equal to, we don't have these actual boundaries all the way yet. So we don't know these values to enough significant digits to make real good comparisons with all of these, right? Because they disagree at some point. So it's hard to make a claim past 7 significant digits. But the big thing was notice that at 7 significant digits is where the hinge point happens, where things start to disagree, okay? And once you notice it's at the 7th significant digit that things start to disagree, you might, after playing around with all of these over and over and over, notice that when we put together the Planck length with the Planck mass, over the Planck charge squared, we get 1 times 10 to the negative 7. Does this mean anything? Does it mean anything to you? What pops into your mind?
Other than why is it 7?
Well, we notice, prefaced with noticing that when we look through all these constants and we're trying to make sense of them, they disagree about what these are, around 7 significant digits from then on, right? And here we have a construction of these guys that is a marker at the 7th significant digit, right? The 7th digit in the number is this guy. It's a 1. Which means, I'm trying to lead it a little bit here, but see if you get, what does that mean? If we notice that our pattern can't be made sense of past the 7th significant digit, and interestingly, you can take these guys to put together something that pops out a shifter at the 7th significant digit, maybe this,
Like it's the maximum resolution.
maybe we have to say it's x times by 1 plus or minus y times by this. Kind of following me? Because we need something to be big and something to be small, and we know how small. We need something to be 7 significant digits. It doesn't play a role, doesn't come into the story until the 7th significant digit. That's what we need now from this pattern. We notice that we can't make sense of these past 7. So there must be another player coming into the picture. But interestingly, these guys give us a player that comes into the picture then. So it's a little hint.
So we're saying that 10 to the minus 7 is the maximum resolution that these things can be measured?
No, they are the maximum resolution to which we've figured out what their numbers are, because we get to them by combining, dividing these together. But you can do it, you can get to this one, we can get to any of them by combining different sets, different numbers that we've measured. And they have different error bars and so on, but still, most of the error bars are way past where the error up here would be. These error bars are in digit 12 and 13 and 11, and these errors are 5 to 7 kind of, right? So, are you tracking this?
Yeah. But then it just means that we just need a more refined measurement of the other constants.
It means we have a system. We have this thing is not just equals to one thing. It's equal to one thing that has a big component, but it has a smaller component somewhere at the 7th digit that comes into play. It's a 2-piece system, big piece and small, but very specifically, the small one's scaled by that amount. Okay? Which is phenomenal because we have the bounds of the form itself that gave us the offset. Okay? And it's just, we're following a hunch and a guess on this. It's a little insight that there's, in the pattern, it's only made sense to the 7th significant digit, and I can use those boundaries to give me an offset at that digit. So now let's make our guess. We've been looking for making sense of the world with these constants. And how I did it, I put in the full number in Wolfram Alpha and I hit enter and see if anything pops up, anything interesting at all. What do I mean by that? An equation that's algebraic, made up of only a few number of pieces, put together in an easy way.
But one question, is that a boundary or just a resolution question?
Which?
The 10 to the 7, 97.
It's a resolution. Well, in this thing, it's a resolution question, right? Like, we can't get better resolution from these on those, but these things give us the same restriction that the resolution was cut off on. So it's a hint. It doesn't, it's a hint now we're going to follow. But
doesn't that imply that, for example, the time boundary is paired off with something really small? There's a pairing.
yeah, it doesn't tell you which one's which, but it tells you there's a pairing, there's some big one and some small one. Yeah, so because it's off by 7 significant digits, it has to be a much smaller contribution. Good. So this insight allowed the question process to suddenly spark really good answers. Okay, but in order for that to really mean something to you guys, I know you haven't wasted years every day asking questions and checking. I want you to get a little impression of what I mean by asking questions and checking. You ask this one, And then you get any answer that comes out looking like it could be made into a story. Anything you think, yeah, if I really tried, I could eventually tell the story of those numbers. Okay, so if it's really complicated, you just skip it from the beginning. You look for the easiest ones and you write them down. And you write down how many significant digits it equals the same number afterwards. Put a box around it, now you did 1. Well, you might have 4. You might have this answer, Wolfram Alpha might spit out 4 different things. It's possible, right? You have to write on all 4. And then you delete this last digit in Wolfram Alpha and then enter again and search again when it doesn't know anything about that digit. Now it's only searching to this accuracy. I did that for every constant of nature, deleting all the way down to say 3, because I need at least 3 significant digits to think the number's got any correlation, right? But to search for that place where things come off and to search for any possible answer. Like, okay, if I can't get the answer to this accurately, well, can I get it that one? I mean, if I can't have all the digits, give me 1 but all the digits. I'm pretty happy. Okay, how about 1 less? How accurately can you actually find something that gets as a representation? That was the game at first. And notice the answers you get, you don't necessarily understand at all right away. You're just collecting answers that might be clues, ones that get you to the same number at the kind of resolution, and you record the resolution at which it gets you to the same number. Follow? So if you have to do this for every single number, that's a lot of time, right? Especially if you're not, if you're not doing it systematic, if you're trying to do it systematically in your head and you're not using computer programming. I wanted to go through and see each one and go through it. So you can make typos, you can do all kinds of errors, but I did this for 10 years. I redid them and redid them and redid them. Couldn't make much progress until I said, oh, wait. Hey, I've been searching and I find the interesting stuff right about here. When all the digits I delete down to 7-ish, it could be 5, it could be 9, but it's always around 7 that things give me some sort of geometric or algebraic equation that I could parse, something I could make sense of. So what if the form is just, we've got some sort of geometric action, so I'll call it primary action, and some set of boundaries that are forming the geometry or intersection, and that's the large thing that's happening. And the small thing that's happening is a terminal action on some set of terminal boundaries. But that set of terminal boundaries is always fixed in our one construction because it's one manifold. It's one balanced system with all 5 dimensions. Okay? So we're going to pick this very specific. I'm going to give this symbol for a field in Chinese. Okay? And this is the structure of field theory. So here's the bounded structure for field theory. We're going to say it's this offset here. So we have this terminal bound, and we have a set of possible primary boundaries that can apply to, this is determined by the constant you pick. So when you pick the speed of light, this is going to be any constant of nature. So this is the prescription for how we divide up the world, right? A big piece and a small piece under geometric action. And now we search for the actions. What are the balances of these partition boundaries against each other? Okay, this is where we're at now. So we're going to hope that when we search with this prescription, that now our answers become something that are all coherently telling a story or a similar story, right? This is how we're going to look deeper into reality for more clues. Okay. It turns out that when we do this, when we pick this structure, that all the constants in nature immediately, let me go a couple more steps. A few more steps. There's a big insight that happened. There's 2 big insights. This is one, and this took me 10 years to get to the point where I knew I needed to be a 2-part system, and one of them has to be offset roughly this, and then was intrigued enough by the fact that this landed what I needed. When I applied this form now, with this exact offset, I was able to get not just, no, I actually remember where I was going. I needed an explanation of what these things could possibly be. So all of these boundaries are always going to be, pick your constant, tell me what dimensions of the constant in, turn those constants literally into the limits of their dimensions. So meters is Planck length, seconds is Planck time, and put them in there, divided, because they're divided here. So take the same relationship, but put them into the scaling of the limits of their bounds. Okay? Every time that's what this is. But a primary action, that action could be 1, it could be 2 pi, it could be 1 over pi, but it's limited to a set of numbers that's 1 pi, 2 pi, things like this, but also J1 and J1 squared. A couple other ones, but this is the main set. You can't go down that low? You can't see? Okay. Let's say the primary actions have a set of things. Well, 1's a very good number. That means the arrangement it's talking about, the boundary intersection, is a unitary intersection. It's just a 1-to-1 relationship, this one divided by that one. And there's no rotating around a circle as we go, it's just a 1-to-1. Okay? So 1's great, pi, 2 pi, J1, and J1 squared, so on, things like that. So now we need to explain what J1 is. That's the next second step. This was an insight where we could now structure a form to start searching the constants of nature under a bipartition structure on a form that's made up of 2 different things but added together, like a plus b to the n, right?
Did you have
Follow
a
it?
reason for how you arrived at those elements, or did you just?
At these elements? Yeah, I'm going to get to that right now. So the second insight, this is the first. This is a structure that we can pattern things out of, and when we do, things fall together. But in order to do that, we have to have a second insight too. When we have this equation, 1 over x plus x, it's x cubed over 2 pi, equals I to the I, the negative pi over 2, minus the Planck mass. This is a transform we're going to call the hyperbolic vortex equation. You can see it's got the 1 over x, the hyperbolic logarithm structure, and it's got the inversion, so logarithm inverse. Anyway, this transform has, or this algebraic connection has 4 solutions. And if you put this equation into Wolfram alpha, it's going to kick out what x can be to do this, right? But there's not just one thing. There's 4. There's 4 things at the same time. And one of them's right here. I'm going to call it J1 and give it that label, okay? And then there's another one right here, J2. And then the third one's way up here, not on the real line. And the fourth one's symmetrically, whether I drew it accurately or not, it's inverse on the line and down there, okay? These 4 solutions represent what again? The solutions to this algebraic structure, right? Yes? We just put this equation into Wolfram alpha. This is I, the square root of negative 1. This is pi over 2. And the Planck mass is the measured value for the Planck mass. This structure with all 4 solutions is, what are the solutions? Somebody say it. What do these things represent in this thing? What are they doing? What are the dots? The roots, okay, the partition constants of the form, right? They're like, this is everything rotating around that and around that, around that, around that, but this is the point that holds still, right? So you have a structure that's held together under that balance, but these points keep it. Okay.
Did you pick that equation, or did you know to get this to the hyperbolic function, or was that a lot of experimentation?
This was not me. This was a miracle that came to me. I was searching this for a long time for something like this. Didn't know exactly what it was. And somebody who, I guess, read in Einstein's intuition, read a forum where somebody had noticed and posted that there was an algebraic way to get close to the fine structure constant. Okay? And by close, they got like, I don't know, I think it was 6 significant digits, which is more close than anything else. Okay, so it's significantly close. And there's a lot of people who have been trying to get to the fine structure constant for a long time, ever since we knew it was a thing. What is the fine structure constant? Well, it's one of these. It's alpha, right? Fine structure constant. And this is the number that's responsible for all of chemistry, right? It's central in the entire organization and structure and scaling in everything we call chemistry. It's right there at the center. The electron's charge, I mean, it's inexplicable. inexplicable in physics. It's central, and it's dimensionless. Meaning, when you write down the number, it doesn't have units. It's a geometric number only. Okay? And for that reason, in this list of constants, it's the one most people would want to focus on, because with these dimensions, if you don't know the story of the dimensions, you're kind of stuck. But if you know that this one is just a dimensionless number, then you know it's a purely geometric number, right? Following so far? Good?
Yeah.
Okay. So I didn't figure this out. What I got was an email saying, oh, I'm sure you already know this, but just in case you didn't, check this out. And I was blown away because what I was given was this, something very close to this. It wasn't worked like this, but it was worked in terms of the fine structure constant instead of the square root of the fine structure constant. But I could easily just rework it to get this, and found, this is the form that gets you real close to the fine structure constant. What would I have to modify it by to get all of it? That's just what I asked, right? So it's okay, minus x. Well, from alpha, I put in this case, I would put in the actual number for the fine structure constant, right? And then solve for y. What does it need to be? And what did it pop out? The number that's equivalent to the value for that.
So that was popped out, you didn't just pick that.
No, Wolfram Alpha popped that out. And then I knew, okay, this is important. First of all, it was already exciting to get an equation at all, any equation at all that you can write down on a single page to get to the fine structure constant. It's not so easy to do. People have published their PhDs writing all kinds of ways to get to 2 and 3 significant digits, right? This one gets real close, but with the Planck mass, it gets all the way. That's really interesting. That's really interesting. So now we look at this function. I want to look at this algebraic form that's telling us a relationship built into something, right? Something related to the Planck mass, clearly. And there's 2 twists here, clearly. So maybe these boundaries have some sort of twisted relationship. Or these pieces slowly coming together. But then when we look here, what took me forever is, once I knew this, I was super excited about this guy. Okay? I was so focused on that one, I didn't really take that one and this one as serious things for over a year. And trying all kinds of questions, searching against that through every constant of nature for a while. Couldn't really find too much, found a few. Well, later I decide, if I'm taking the algebraic form seriously, I can't just look at one solution. I have to consider all 4, right? You don't get to pick one or the other, otherwise you didn't get to use the whole geometry. So now I'm getting interested in this number and that number and this number, and there's a little story about discovering this one connected to the mass boundary, but that really got me excited. But it woke me up, more importantly, to I need to be checking against all of these partition constants. Why? Because Wolfram Alpha, when I ask it questions, it checks against all the numbers it knows. What are the numbers it doesn't know that I care about? Well, it doesn't know about the actual numbers we want for these, and it doesn't know about these partition constants. Well, that's only things we've introduced. Okay, so right here, we need to ask every question, but we need to ask it by pulling out this, or pulling out this, or one of these squared, or one of those, to see, now you're asking it with that thing in it. Okay, then it took another while, I can't remember exactly how long, but I asked all the questions there and found a few more, okay? And then all of a sudden, I realized from 0 here to there, this is J(R). J3 is equal to some negative x amount, positive y amount, right? We can break it in Cartesian coordinates to x and y amounts and give us the values that they have. Or we could at the same time represent it by an angle and a radius. So we can set it equal to J3 can be in Cartesian form, or we can set it equal to J(R) times by e to the J theta. So this angle is going to be J theta. So now we have 1, 2, 3, and 4, but we have 2 framing ways to talk about them. If we change into polar coordinates, then J1 and J2 are still like they used to be because they're on the real line, right? But if we're in, that's the only difference. In polar coordinates, J1 and J2 are exactly the same, but we're going to care about the R and theta. And if we're in X and Y coordinates, we'll be at J1, J2, and we care about 3 and 4. Got it? So just two different transforms or ways to talk about it, but the numbers, this number and this number, are also in here. Wolfram Alpha had been kicking them out every time I'd asked the question for years, and I'd just been ignoring them. Right? When you don't know what to look for. So now, when I went back and asked the questions I've been asking for years, and finally made a couple things that were, okay, these answers might be good, but the rest of them, I got the best I could get, but they weren't very satisfying yet. When I asked it with JR, most of them were in JR, a couple of was JR theta, but JR, pretty much all of the pieces came together into clear pictures now. Okay, so this was my procedure. I had to go through it many, many times over and over, so it's much faster now if you kind of know what the goal is. We're now talking about a pattern that we have now caught between all of the constants of nature that is in two parts, a big part and a small part, and the scaling of the small part's always fixed by 3 of the scaled parameters of the 5, okay? And that the external connection of that domain is maintained under this algebraic logic, which divides by these 4 partition constants. Yeah, anyway, it really got easier to tell the story if I try to tell it in JR and J theta. A lot of the constants just become, well, we'll go through some if you want. So we have our 4 J's, and we're trying to let them sink into our heads a little bit. And we have our J R and J theta that we can represent J3 and J4 with alternatively. They're not new content, but they're another way to represent it. We're trying to understand the relationship these things force into the world. So if you're assuming that the algebraic equation is the structure that's maintained externally, then these are its partition constants. But what does that mean? Well, first it means that we have a balance. This is equal, anybody know? If we add all of our partition constants of our construction together, just add them together, 0. That's interesting, but now you know what I mean by balance. These 4 partition constants are creating a balance.
On the negative side, opposite each other, so they cancel out, and the 2 are on the positive side. And I can see when you collapse the 2 on the negative side, they would cancel each other out.
Yep.
Yep, I can see that.
Should have kept it. Okay. All right. Well, so that's interesting. You could visualize that pretty close to if I draw accurately, right? But also then, okay, well, if we're going to take a sums, because if we're talking about a connected manifold, a form of any sort that closes itself, sums should be interesting. And the next thing, products, right? So let's take the product, times by J2, times by J3, times by J4, and we get, guesses?
Let's do 5.
I'm good at memory. 2 pi. What does that mean? Wait. What does this mean? The product of our partition constants, the roots of our form, is a circle, right? And we're starting to learn how to algebraically read the geometry. Now, you might want to ask, if you know about doing algebraic forms, let's ask about the quadrants. What's the quadrants of this structure? Well, you find that by squaring all of its zeros, all of its roots, and adding them together. And this is fantastic. Now think, what does quadrants mean? The thing, the form you are subdividing. We're cutting it up, right? What are we cutting up? Now this algebra, there's more. This 3 alone are enough for us to understand we're in a field. What kind of field?
Circular field?
Okay, it's circular to a closed field, but it looks like it partitions into perhaps 2 circles, somehow making a sphere, right, over a balance. And we only need these 4 things to tell that story.
It's a closed why is that a minus?
Why is that a minus? Because quadrants is the sum of the squares or the difference of the squares. So I could also now put minus squared, minus squared, minus squared, minus squared, and get plus 4 pi. It's both. It's a negative 4 pi and a positive 4 pi, which is a really good point. So its quadrants is both. It's a sphere and an inverted sphere, or a projected sphere and a regular sphere, right? It's which we would call, or which would call into mind maybe the Riemann sphere, right? So we have a quadrant that's spherical, but in both directions. What does that mean? It's spherical in both directions, right? The quadrants, negative 4 pi or positive 4 pi. In the real Riemann sphere, there's structure as we go down in scale. It turns into, a torus-bound structure that gives us all Clifford algebra. But okay, so where are we going now? These are our insights. So we've got this hyperbolic vortex connection that's partitioning this domain in an ideal symmetric way, closed way, right? And that domain is partitioned into a big piece and a small piece. Like as a throat, like a vortex, there's a throat vortex, and there's the back end of things, okay? So we have both pieces, and when we try to now interpret these constants in nature, the numbers that we've measured that tell us most about real reality, then they all become interpretable. That's the first step. Is any interpretation we pick right? That's up for debate, right? But they aren't so easy to find a solution for at a get-go. But the fact that this one construction gives us a simple solution for all of them is profoundly exciting, right? It means we get to now busy ourselves with the interpretation part, with the updating the way we conceive reality. We're not stuck, because anybody can go check. Anybody can follow this algebraic equation, put in a constant of nature, put in its number on this side, right? With the scale and everything, you put the whole number on that side. Then you put in the boundaries of the dimensions of the constant, so in terms of the Planck constants, and solve for this. Could be 1, could be 2 pi, could be pi over j, could be a few things, but solve for that. And then that means whatever this is, it's going to tell you the geometric action occurring on the intersection of these boundaries, right? So you can start to interpret the form a lot more clearly. On the back side, we have a fixed set of boundaries. So there's a different set of arranged boundaries on one side, but it always closes in the back end on the same set, okay? So the whole collection have a back closed set. Great. Well, where does that put us now? Why are we all gathering here in the physics monastery talking about this stuff? Because we've made enough insight from this process that we think we have a closer story, in fact, a story that's starting to get some traction, right, in making sense of the world. So let's start telling that story. Of course, our process is to tell this story and then go back now and go through all the numbers and check again, try to get more clarified, okay? So we're not claiming an end story. We're saying this is where we're at. Let's leverage where we're at to keep going, because figuring out these boundaries all the way and understanding the rules of exchange between these boundaries means we become empowered to do something that seems like only gods could do up until now, right? What is that? Name something. Well, what about the charge boundary? We knew nothing about the charge boundary until more recently in history, right? But now electricity is the dominant form of things we consume, right? It gives us so many things. So understanding the shape of the charge boundary, understanding the shape of the electron, understanding the connections and the partition rules that these things play will give us the ability to engage with them in a new way, right? We didn't know about electrons, now we do. We have a whole new level of reality to engage with. We don't know about the Planck time boundary, the Planck length boundary, and so on, and then we become into possession of a story for them. That story means we're peeking inside the clock and seeing the gears. And the more we stare at the gears, the more we see how it starts to work, the more we point the machinery of our consciousness at this mystery, the more we can see, the more we give it to absorb, the more it will make sense of it. And the more we understand this structure, the the more we can make anything we've ever named. It's like the ultimate prize, right? Because achieving clarity on what these dimensions are elevates us to something that no longer has to worry about resource, control, demand. Why? Gaining access to be able to logic that it takes energy from this boundary, not just this boundary, is 10 orders of magnitude larger than the charge boundary. Right now, all of chemistry, all the ways we extract energy in the world are coming from the charge boundary. There's 10 orders more available in the mass boundary, and we haven't figured out how to extract it because we don't know how the gears are fitting together on the black box of the inside of quantum mechanics, right? When we figure that out, we have at least this on the plate, right? We have fusion that we can then control in sequences because we know what's going on the inside. And where do we get the fuel source for that fusion? From anything that has mass. That completely changes everything about the world we currently live in, right? The restrictions of the current world make it so that most mass around us is valueless. Most of it's garbage to us. We practice ignoring it. And when we can access the mass boundary through this logical exchange and convert it all into energy the way we want, or maybe just convert it into a transform to make it do something for us, the things we can do become completely new. Okay, so this is the goal. Now, are we claiming we're a week away from the goal, a month away? We have no idea how long it's going to keep taking. We know that what we're doing is we have a method to ask what's going on, and we get answers, and then we try to correct and make our model clearer and clearer. But that method has so far led to a lot of insight. And here's what the story, I'll try to tell it in a short form now, has come to so far, okay? If you're starting with a void of random waves in it, an infinite void, a collection of random waves, there's no essences in it, meaning there's stuff happening, but there's nothing that persistently happens. There's nothing you can go measure and then come back later and say, yep, it's still there, because it's just random noise. It doesn't do it again later, okay? So we're going to think of this as a structureless void, structureless medium, and we're going to ask the question, what's required for structure to come into existence within this medium? And more specifically, what's the minimum required? Right, that's kind of a good question to ask, right? Why? Because we want a manifold. If we're inventing a universe, we want to first come up with some sort of coherent sense of what a universe is. It's going to be a thing that's persisting, that has properties, that has characteristics, that has relationships built into it, okay? And finding those properties, characteristics, relationships is what it means to discover it, okay? Imagine you're putting together waves and you're trying to figure out how to put together waves inside this medium so that they don't create any open bubbles in the medium, okay? But they slide along each other in a way that as soon as they finish one loop, they're back to where they started so that they loop again. And they close on themselves and they close on themselves. What minimum form could you possibly use to close back on itself? Well, in geometry, we call these forms manifolds, right? And one simple example of a manifold would be a torus. And to show how it's a manifold, if you take a sheet of paper, maybe I should get a sheet of paper. You got one? We imagine in topology that we're allowed to stretch things as long as you don't pinch them, no sharp corners. Okay, so if we take a sheet of paper, and now it's a two-dimensional form, okay, if it was flat, well, I can roll the two-dimensional, or it's a two-dimensional form that if you were an ant, you would walk along and you would say, there's an edge here. Okay, that's a definite, it's a place I'm going to say is special compared to other places. Why? Because if I keep walking like I used to walk, I'm going to fall off. Okay, well, I can do that on 4 edges here, if the ant's on top, right? Well, if you roll it up and glue these edges together, right, then now there's only edges here for the ant to walk off. If it tries to walk this way, it's just going to keep going around, 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 and not see this magical point where everything's different at the edge. Okay, Then if you take these, and if it was stretchy, I could put it together like a donut. Now there's no edges for the ant to walk off. It can walk forever in many different directions, but not come off it, right? Okay, thank you. So that's a two-dimensional manifold. Okay, it's a boundary of 2 dimensions that you can walk forever on it. Never go off an edge, okay? If you want to go higher dimensions, we need to start with something with more things in it, and we want all those things to close against each other, meaning the set of rotations has to collectively end. All right, so once again, we're starting with our infinite void, and we want to ask, what sort of way could we distort this void with some sort of wave actions that minimally makes some sort of manifold that closes again on itself and continues the distortion once we've made it, okay? So this is going to be our minimum universe because it's our minimum form that can keep itself. So that's called the hyperbolic figure 8 knot on the inside, right? Meaning how this form behaves depends on if you're on the inside of its division boundary or the outside of its division boundary. What its shape looks like is different to you based on either or. And you can't cross. If you find yourself caught in the outside domain, you're never going to go into the inside domain and vice versa, okay? But so it's a structure that literally induces a boundary and therefore defines an inside and an outside. That's the simplest thing to say about it. The outside structure of this, so instead of the form, the shape it has on the inside, things are rotated in its construction on the outside and projected out. And the shape of this projection is, on its largest scale, just spherical. It's waves coming from the inside, some balance, everything's shooting out, and it gets quieter and quieter as it comes further out. And at some point, there's just no more action from the balance. Now we're back into the random void. Okay, so spherical, but minus the boundary, meaning the boundary's quiet, it's not part of the action, it's where the action dies. And now the boundaries on the inside are where the action is. Okay, and what's the shape as we go to the boundaries on the inside of the exterior domain, the exterior projection of this form? It's called the N hypersphere of maximal volume. This is a fun little point, so let's stop here for a second. We're devising a structure, a geometric form, that is literally the smallest little distortion you can make and still continue to be a distortion. So the smallest distortion on the inside, which takes the outside and makes it rotate against that tiny distortion, but makes the outside much bigger because it's a small rotation, right? Okay, so we have asymmetric forms balanced against each other, but the external one is called the N hypersphere of maximal volume. This one was the minimum volume. We've created one form that defines both the minimum volume complement possible in geometry under self-balanced waveform action, right? Or just under geometric decomposition. And its exterior expression also defines the N hypersphere of maximal volume, the most voluminous spherical structure that can exist. What do I mean by that? How could there be a maximum one? Why couldn't you just go bigger, right? Is this the dark one? That's the light one. Let's go green. When you plot the dimensions, so as you make n go up in dimension for the hypersphere, so you can represent any number of dimension hypersphere with this form. But as the dimensions go up, and this is volume, this way, its volume goes up and then peaks and goes back down. You keep going up dimension and the volume of the hypersphere you're talking about gets less and less and less. There is a very specific dimensional point right here that has the maximal possible structure of volume that it creates. Okay? So this is what we're saying. We're creating now the smallest possible internal distortion thing wrapping around on itself, called the hyperbolic figure 8 knot. And its external expression creates then, in counterbalance, the N hypersphere of maximal volume. That's a great starting position for our simple universe, right? Great. The inside of this form has 2 different orthogonal actions composing it. The outside is four-dimensional, made of two different circles that are restricted together. This is on the internal boundary of the outside. And that connection between two circles is chirally bound, and it's asymmetric. So it's one circle and one that's way smaller, and they're connected. So it can be through, it doesn't have to be at the edge, they can be linked in between, right? But they're connected. So whenever this one twists, that one will twist, okay? The fact that they're asymmetric, that one's way smaller than the other, means what? It means that as this connection between them is wound, or as this thing winds around, the small one winds so much faster, right? It really winds up that it locks the degrees of freedom for the second one's connection to it. So instead of this one being able to do anything like it could before, now it can only sweep around like this compared to the second small one, okay? Because it's chirally bound. What does that do? That means as you go away from this scale rather quickly, your structure only has 3 divisions in it. Instead of 4, it starts out 2 and 2 for the 2 dimensions of each circle, okay? But then it encapsulates a volume, twists together a volume that really quickly only has 3-dimensional component. So we get the 3-sphere internally decomposing into 2 different circles for what we would call the torus, or the Clifford torus. So the internal bound of this structure is the Clifford torus, or the intersection of 2 circles, but it's the asymmetric Clifford torus. So one of those circles is much smaller than the other. Okay, so this is a starting story, a setup we have for the simplest universe we might want to imagine, right? The simplest construction. What's that universe doing once we invoke it? Well, it should just keep doing what it was doing. Meaning it's always internally rotating and breaking into pieces that then push into the other places and fill the back space, and all the pieces are closing one complete set of actions, right? Okay.
So we can say that this is an implementation or an instance of those 5 dimensions as base classes.
We can, but we haven't got to that point in the story yet.
Okay, but
Yes.
I guess
So
I'll
what we
leave it
want
there.
to do now is we want to find how is it that I came up with this story about a simplest possible universe. But really, if you pay attention to what I said a long time before, I came to this story from these constants. How? Now, before we get to how, let's repeat what's happening here. We used the constants of nature to get to to understand these better. We end up getting to a story from our investigation of the constants of nature of how to interpret these things. But the interpretation forces us to say that we're talking about a structure that's balanced on the minimum possible manifold and externally creating the counteraction to that, the maximum possible n hypersphere, okay, or the maximal volume. So we have a minimal volume and maximum volume complement balancing each other, but both of those complements form or define the minimal volume complement possible and the maximum volume complement possible.
The maximum volume, this seems counterintuitive. Why doesn't that just continue?
You might think that same thing for minimum too. Why is there a cutoff, right? Yeah, because the minimum maybe makes more sense. You have to get out of your own way in order to stuff things back together. But maximum, because it's a maximum volume of structured form. You can't get a form that has more volume and is structurally coherent. You could in your mind imagine a sphere that's infinite radius. But now I can come around and say, all right, but how does that sphere keep its structure? How does it stay as a sphere? What's balancing the spherical structure inside of it? So give me the explanation for its boundary and its internal contents. This is a form that you can give an explanation for its boundary and its internal contents, and the explanation is the same. The boundaries partition its internal contents, right? And it's the first form we can do this for, but it turns out that first form maps to these. This is a mind-blowing thing. That simplest possible universe you could create in geometry happens to have the same exact boundaries as the ones we've been calling the Planck constants, the Planck time, Planck length, Planck charge, Planck mass, and temperature. So the 5 dimensions, the most mysterious aspects of our reality, are the dimensions of its bases, or what is time, what is space, and so on, right? These things are coherently maintaining the simplest balance possible. That's a really beautiful solution. Now, I haven't given you the numbers to conclude that yet, so now we can go into numbers. Before I do that, let me entertain some questions.
So with this, the maximum and minimal manifolds, the volumes, when he asks why is there a maximum, are you saying because there has to be a minimum, since they have to get out of its own way, it has to be balanced with the maximum?
Yeah, the maximum is the offset of the minimum. It's the inversion of the minimum. But the fact that there is a maximum is a shock, right? Because you could be able to think in your head, I want an infinite radius sphere. Fine, but we're only talking about forms that are self-closed logically, the forms that generate themselves, not just imaginary ones that with no explanation. Yeah, and it turns out, as an awesome insight, that in geometry, there's a claim that there's a minimal form and a maximal volume form. Right? Okay. Those big insights, how we connect them, is still up to us. But this is the way I'm connecting them, that this is actually what's going on. That our universe is actually just the simplest possible geometric structure, okay, that you can create in this way, and without having to always interject energy or something to keep the system going. Okay.
You're proposing this as an ideal fluid. You spoke about this flowing field.
I conceive of this in my head in fluid terms, but I really should point out that what's happening is it's showing that if you ask, well, what's the fluids this in, you're missing the content of the question. Because if I answer the question, this is the fluid, I didn't answer anything. I can just make something up as an answer. The thing is, the only way you can describe or understand the medium is understand all of its attributes and relationships. So once I've given you all the things the fluid can do, and you know all of its characteristics and so on, now I've actually answered what the fluid is. But a priori, it didn't have characteristics.
Which is the entire structure itself at that point. Like, it's the whole structure. It's all one thing that you have to be able to take.
If we're in a form or a universe that we're calling now the simplest universe, right, then everywhere in that universe is going to be coherently balancing all 5 of these boundaries under whatever the rules of that balance is.
Right, so yes, there's some actions that act in a way that feel intuitive to fluid dynamics, but we're not referring to it as a fluid.
Oh, okay. I'm just trying to disentangle. A lot of people have read Einstein's Intuition, a prior work of mine. It's getting about 10 years or more now old. And in that model, in that book, I tried to explain or catch us up to the insights we've made through astronomy and math and physics, to the worldview that we currently have. And then I continue to make a guess of where we should go next to try to make more sense of things. So I propose this model called quantum space theory, that it gives us a visual way of parsing conceptually, visually, what the action of gravitation is, right? So you can understand gravity without having to go into a 2-dimensional warped sheet representation. You can get the whole 3-dimensional effect of gravity. But the problem with that model, very obviously, is it has boundaries, the surface of the bubbles, all over the place that you don't have an explanation for. They're magical spheres, right? Now, of course, that's a problem. Every model has a problem, but maybe you can come up with, find out what the reason is and get rid of the magic. But at that point, that's how it stood. So what I needed to do at that point was, I have a justification for all the actions of gravity in terms of these density fields, but I have these gaps, inventing boundaries in order to have the density fields. If I could only have boundaries without gaps,
Enclosed.
like a manifold, right? So, I mean, I don't know if I've even heard the word manifold 10 years ago. I don't think I had. So, I didn't know it'll be looking for something like that. But still, this is the story. This is where we're at right now with my interpretation of the story. But the exciting part is I got this interpretation from the measurements, right? That's the real point that I really want to harp on, is that we now have a method, whether you think I'm right or wrong with my interpretation, you have a way, we've found a single pattern that gives us a way to ask questions about the measurements we think best represent reality. The things that physicists are no longer getting paid to make sense of. We now have a way for anyone in high school that knows how to use Wolfram Alpha and is comfortable with plus and minus and divide and multiply. That we're just talking about the basic intersections and rules between intersections of these base dimensions of reality. But in a way we can now decode, or anyone can decode if you're slightly familiar with the math, right? It's a very simple system. Remember, by simple I mean, this is our argument. We have a partition action. We have a primary partition action, we have our primary set of boundaries, and these are going to be much bigger than the smaller part, so a two-part system, and this is always going to be our pattern. So a terminal action, and then a very specific set of terminal boundaries, which we remember are made up of these. These will always be made up of these also, but this is made up of a very specific set of those fixed, okay? That's a simple, a simple way to tease apart what reality is, but it's nice because here we have a structure that made a boundary, and that boundary is explaining the internal divisions and the external divisions against each other, right? Here, this is just about the external domain. So why do we have a two-piece structure in the external domain? Because remember we said it was a connection between a giant and a small circle that are chirally bound. So they go through each other, and at least they can be touching at one point, or they don't have to be touching, but going through each other, right? So with that bound, with this Clifford-Torres logical bound in your construction, and with knowing the scaling parameter there, all you needed to know was to apply the boundaries to the literal Planck constants, to use this as a prescription to look into nature further. So with that note, I can list all the constants and the best I've been able to pull the information out so far, but with the goal of maybe inspiring someone to say, hey, that one isn't clear enough to me, I'm going to find a better answer to that, right? So many of us are playing this game. And that's what all of us here are kind of excited about doing. We want to finish telling the story. So I need to move the camera now and go over to some of the constants that are up, because I don't want to write all the numbers forever and everything. So let's stand up and go over here for a second. Okay, so these are the constants of nature, listed here and listed here. Okay, these two columns are literally all the constants of nature, and they're prescription, like the constant, the symbol we're used to using for them, and they are parsed apart using this simple prescription. All of these pull apart into exactly these forms. What you would notice on the left-hand side is just components of the Planck constant boundaries, and it has over here 1 over J1, 2 pi over J1 squared over 2 pi, pi over J1. See, it's a very simple pattern here. We got pi's and J1s on the right-hand side, or just ones, right? And on the right-hand side, we're getting some things that really pair up. Now, before we try to tell ourselves we understand these things, we're just trying to compare them, right? We're trying to notice the similarities. Let's focus on this one. If you see here, it's got a primary action of pi, and this one has a primary action of 1 over pi with this J1 squared on top, okay? So it's like inverse except for this J1 squared. The boundaries is the Planck length squared and the Planck mass. Down here, Planck length squared, Planck mass on the denominator. And up here, Planck time and mass of the electron. Down here, Planck time and charge of the electron squared. So they're almost inversions of each other, except we swapped out the mass of the electron with the Planck charge squared. And if I pull this with the Planck charge squared, J1 pp equals the charge of the electron. So this becomes the electron's charge squared, and that's the electron's mass squared. And that's the only difference other than the inversion. And when we look at the right-hand side in J theta squared, the first one has a primary action here with the square root of zeta of 2, and the charge boundary has a square root of zeta of 3. Now, I don't know, do you know anything about the zeta function? Okay, the zeta function is like the prize gem of all of mathematics, to solve the Riemann hypothesis, which asks about the Riemann zeta function, which is right here. Hi. So the Riemann zeta function has several definitions. One is it's an infinite sequence of inverse powers, like zeta of 1 is 1 over 1 plus 1 over 2 plus 1 over 3 all the way to infinity. And zeta of 2 is 1 over 1 squared. So we just added, this used to be to the power of 1 at the bottom, and now it's to the power 2. So you could put any number in that you want there, and we have to put them all here too. And it'll then sum it all up, and it tells you what the answer is. There's a lot of interesting features in the zeta function, of course. Zeta of 1 is infinity, zeta of 2 is pi squared over 6. Think of that. We're just taking the squares of all the integers and inverse of all the integers, and you get pi squared over 6. Phenomenal. But this function itself is just equal to a product or a sum. It's both of these. But when we think about it in terms of a product, it's the product of all the primes. 1 over 1 minus every prime to the negative s. So pick any s, and that will be true for all the primes. So this is a function. It's actually, we've discovered it's like the function of all functions. It's really better to say it's the characteristic space of functions, okay, that connects both sums and products, but is responsible for the structure in the primes. So the reason it's such the superstar question in mathematics is because if you knew the structure, if you could understand how to interpret and richly understand the structure in the zeta function, then you would understand why the primes, if you understand the zeros in this, you understand why the primes are spaced as they are, and therefore could predict far more things about, or would understand far more things about the inherent structure of numbers in nature. Okay, because the prime numbers are like the backbone for all numbers in mathematics. Okay, the zeta function itself is like a dual form of the gamma function. 1 over the gamma function times by this whole integral here is the gamma function except for the minus 1. So e to the x down here, we add a minus 1. So it's really the gamma function divided by the gamma function that makes the zeta function except for this minus 1 in that denominator. There's a little offset. So if you can make sense of the gamma function, then you should be able to make sense of the zeta function. So it's like making it simpler as two-dimensional or reducing it in here. And to make sense of the gamma function, you need to know, or what the gamma function is talking about. It's a transform of the factorial function. So factorial means give me a number, and then I'll break it up into all the numbers below it, including it, and then we're going to multiply all those numbers together. So now we know all the possible arrangements available to this guy, to this thing that can be decomposed into that many pieces. All right. But if we want these arrangements to also close, then we need to use one of them in the set to twist around and loop. So we need to subtract one. So if we subtract one first and then take the factorial, it becomes the function we call the gamma function. A big benefit of the gamma function is when we only use this function, it was defined at 1, 2, 3, 4, 5, and so on, but it wasn't defined in between them or in the negatives. When we use the gamma function, it's defined everywhere in 2 dimensions, like in the complex plane. So we can now get a value everywhere. The main reason we really like this is it allows us to look into this. This allows us to only look at 1 and 2 and 3. This allows us to look much more richly, okay? But the big question or discovery is that the gamma function itself shows us all this complex structure we didn't expect. The world's being held together under a logic that looks far more complicated and weird and beautiful than anyone was imagining before we could look at this, right? And this is just in the logical structure of math. There is no physics constraint put in this. This is just a logical constraint so far, right? These logical constraints, in the ideal situation, should also be responsible for the geometric constraints of the form that you're calling your universe, right? That would be ideal because why? Because you only have operations, things that happen in your universe, plus and minus, divide, multiply, and powers and logs and so on, right? These connected operations. But if the form itself defines the operations, then they become synonymous, which means you can understand both of them really richly, right? Okay, so back to the constants over here. This is where I've got the story 2 so far. Let's break this into pieces. We have the minimal arena, which we're claiming is the hyperbolic figure eight on the inside and the n hypersphere on the outside. These are the 2 on the inside, and these are the 3 on the outside, and that projects to what we're going to call the 1, because it's the reference. Of this form is just the reference form. So this reference is internally decomposing these 5 ways, okay? And these numbers tell you, these have to be whole numbers, because if you're breaking up into a certain number of pieces, they need to be whole number pieces. But the rotation all those pieces are under can be any different value. So these have to be whole numbers, and these rotation amounts can be, well, we have to solve for them. Okay, so I got these equations from the values of the Planck constants, connected them to this structure, and then assumed that it was right, which allows me to now calculate the rotation values or the values of the Planck constants to all the remaining significant digits. So the green digits here are now what we get by assuming the structure on top of the Planck constants, okay? And the black digits are what we had before. Okay, so we're really improving our claim on the Planck constants, but we're also showing that all of them are just hyperbolically divided, hyperbolically balanced. That's what these division boundaries are representing, is a 5-part hyperbolic division and balance. Great. Here's our hyperbolic vortex equation again with its symmetries inbuilt, okay? And this picture is the same as this picture, and it's the time boundary, this one here. It's, to be more exact, if you take the inner part, so before the e to the 0th rotation, take that whole equation and put in a z or 1 over z, so a complex number for the argument so it can plot it, and it turns into this picture. Okay, so this is the structure of what the time manifold action is doing by itself. If we pull them all apart and just look at one at a time. This is what the time one, or the smallest resolution of the manifold is. This is what the next resolution, or space. This one's charge, this is mass, and this is temperature. And it might help to peer into it by looking like this. Imagine you took this figure eight up here, this one like this, and you were separated from that one and pushed it inverted out. Then this picture starts to look a lot like that picture. Now imagine you cut this one and invert that one, and now it looks like this. Okay, I'm just trying to make a little bit of connections here. These forms are all supposed to be one part of the picture, but all 5 of them together now is the picture we want to make. The inside, these two come together to make this shape. The outside comes together under this balance, but we need to get the exact picture now. Is it many copies? We need to get an exact picture, but this is what we know. We have this exact balance, which is conic and inverted conic, right? Both of these are the same cage in the middle. But there's 2 forms. This is the hyperboloid of 1 sheet, and this is the hyperboloid of 2 sheets that this breaks up into. This is the base of what we call hyperbolic geometry, okay? So whenever you have something under hyperbolic balance, it will externally be separating into 2 different metrics, literal metrics. These lines on here are there to remind you these things count as metrics, okay? Because if you're on the surface here, you think these lines are flat. It's a metric space that you can literally measure. But there's 2 of them. It's dividing it into 2 different metric spaces that are under balanced together, okay? That's what the hyperbolic space does. Now, Einstein knew we were already at this. So we're used to cones, we're used to using light cones to represent our construction reality and so on. But I don't think we're used to visualizing that this is really or literally representing a separation in some sort of medium or fluid, or the breaking apart of the pieces of a manifold. Okay. There, I don't know how much more detail we want to go in without using Wolfram alpha. But this should be enough now to be able to stare into these things and try to algebraically read, what does this constant represent? What does that constant represent? How do they relate? You can probably see the relation between those 2. You can probably see the relation there. You can probably see the relation there, right? You can probably see the relation there and between there. Here, the speed of light. First part, Planck length over Planck time. The second part, 2 pi, divided by the derangements of the space boundary, the 35, and r squared, which is our radius of our external division construction. Okay, that's a lot. I'm winding down for talking. My point is, here on one structure, we're able to list now, under this one form, a bunch of things that are really popping up with a lot of symmetries that couldn't otherwise be explained. That's a lot of magic, right? But there's some down here that aren't matching up with everything. So, it could be wrong, could be right, we don't understand them. That's where we're at the quest. I've ordered them basically in my confidence arrangement. So, and also some of them we don't have very many significant digits on the back end, so no one's going to have much confidence in those. But still, this is the way we're trying to look into reality. That's the goal, right? Or that, I guess, the main point. We have a prescription that allows us to individually start asking questions about reality and trying to find an algebraic solution that can be interpreted. And when we do, we get this structure that's given us an infinite power tau of I, that's based on the factorization parameters of our hyperbolic vortex connection, right? That's literally just dividing up the world into twists and turns of these derangements. It's just putting this structure together. That's the whole thing. All of these expressions are inbuilt forced expressions by the relationships by these 5 bounds. That's what it's saying. And now we can parse them. Literally start to understand what the zeta function means in terms of these boundaries being connected, right? We can make a lot more sense of what's going on by being able to ask questions instead of waiting for some next magical lightning bolt to strike us in the head. All right, I'm not going to go into this part yet. I'm getting worn out. I'm going to take a break from talking, but this is where we're kind of at in the picture right now. And our project is to code these arrangements maybe find improvements on them, but to be coding these arrangements into a computer program that can model the actual whole set of symmetries and sheathing forms, all the way things are breaking apart. So we wanted to gain visual access to the whole form, not just in pieces. This is pulled apart. We even need more visual access here because you have to zoom out all the scales for these pulled apart pieces. But we want to put it together in the computer, and what does that mean we get to do? If we succeed, if we can code this logic, which it looks like we can do, it's already looking like it's something that we can understand, right? But when we code that, what does it mean we can do now?
We create a virtual universe.
We create a virtual universe based on the exact same laws that our real universe is based on. We have a way to push into reality and have it push back with the right answer. We have a check. We can actually become less blind.
As a matter of fact, from all of your explanations and hearing it over again, I came up with an amazing insight that.
All right, is it your turn?
Yes.
Good, because I'm done talking. So he's going to explain now a little bit of our project of how we're trying to put this into the computer and to model it.
I can erase this, right?
Yep. My right turn. Oh, let's give him the microphone.
The best part of your whole explanation is it just made me think of it a different way. We were talking about the base classes. So we have time, space, charge, mass, and temperature, right? Just thinking of it from a programming point of view, we actually have one more thing. There's functions that bind these together. So let's think of those functions as objects. Okay, so I'll just put F. And this function binds this. We have some other function that binds this, and so on. Right? Here we have an atom that uses multiple inheritance. In here, because of these functions and the way they act together, I'm not quite sure how we get there yet, but somewhere inside here, that would define the nucleus, all the gluons, the quarks, all the interactions, is something having to do with the way these interact, right?
It's exactly to do with the way they. In fact, the concepts of nature are the something. They define the functions between them.
Programmatically, that's almost exactly how I was.
The gluons would be just a geometric constant, right? Not really a physical thing.
Gluons, yes, yeah. I think you said neutrinos too, right?
The neutrinos have to be in there somewhere too.
Of course, they're all wrapped up in those 5 interactions.
But now we have an atom and another atom that also inherits from these same things, right? Time, space, charge, mass, temperature. Another one. We can think of them as, and along with their functions that bind, we can think of it as another instance of multiple inheritance for a new atom.
Okay.
Now, if we can get any instance of this, like let's say we take the charge, right? This is made up of the charge. Programming-wise, this is an object. So we can get the charge out. Here's the charge. And we go to this atom, and let's just say we get the mass out. I'm not defining what. And we pick one of those functions that has the interaction between the two of them. We can now dynamically, I don't know if we can fuse, if we can create new atoms, but we're basically, we're taking one atom and interacting one of or more of the dimensions with another atom with one or more of the dimensions, and it creates a new thing.
Sad, do we just have one specific formula between each one of those? I mean, how do we compare them up?
No, it's just simplified.
Yeah, I'm simplifying.
We have all
Yeah, there's a lot of them. But the thing is, there's also a function here, right? Like that.
There's a right? So,
connections between many.
right, so,
Multiple connections, right.
and in fact, we would have to diagram it. And in fact, in 3 dimensions, we can probably see it better, right? And the same thing here, right? The same thing on this side. It's like, a view of all the functional interactions. And it has to be that when 2 atoms interact, probably when we're dealing with chemistry, we're getting the charge out and the charge out. We're interacting the charge against the charge. But for fusion, we're probably getting a mass out and we're interacting a mass against a mass. There must be some function that has 2 masses, although I haven't seen it on the board. Is there a function for 2 like kinds, 2 charges, 2 masses?
Yes, there's several of them.
Okay, then.
The mass of electron, the mass of proton being divided, and neutron and proton and so on.
So then the way the program would work is we get this atom, we interact it, we pick which dimension we want to interact, and we pull one of the functions that we know are available, and out comes the answer.
Yeah.
I think this is how we would create. Everything would be dynamic. That would solve the problem we were talking about yesterday, where we want to be able to have objects transform into other types of objects according to the actual laws of physics. And this would do that, because we would basically, when we create something new, let's say we did a fusion, we went to helium, so we're going to end up pulling the dimensions out of here and the dimensions out of here in a new form, and some of these components are going to be left over. And we can quantify that. We'll know exactly, after these functions execute, there's going to be a leftover. I don't know if it's a neutrino coming out or... So I think to build this, it's just the 5 dimensions and the library of functionality and some rules that define which functions are allowed on which dimensions, which means we reuse those same rules over and over when we interact multiple atoms. So it would create the atom, because...
We're saying that the whole thing actually is the atom. Before we were imagining atoms are like point particles with magical properties. We're saying there's no more point particles. There's boundaries of manifolds, and the scales of those boundaries, the shapes and size of those boundaries, are the properties we're talking about.
Which makes it easier to explain why any atom with its magnetic and electrical properties can have infinite extent, because it's connected to the entire geometric object.
Well, it's really saying
And-
that the universe is the primordial atom.
Yes,
Yeah,
that's what it's
The
saying.
rest of the stuff is inside.
That's what it's saying.
Yeah.
You're right.
And the thing that's exciting about this is that we just mix these, between the inheritance and the functions, and mix it together. We can create the atoms with it. We can bind atoms together to get chemistry. And we reuse the same functions to make new atoms, do fusion. It's just which ones are interacting. In fact, we should be able to, if we have all these functions, we should be able to figure out what will fuse. And then once we have virtual fusion, we know how to do it in the real world.
The quantization is just the log capacity of the unit disk, because that dictates what our lattice points that we can fit inside a surface is.
How we're able to divide them.
Yeah.
So we would have a known or a fixed scale that comes from that. You're talking about that we could have
Yeah,
it cut
so
out that.
it's so the 2 things, the video I sent on log capacity of the disk, and then the fundamental pair of pyramids, which is how you combine modular forms and elliptic functions to define your coordinates.
Can we think of it, we compare charge to mass, temperature, time, space, and charge again. Put the G back in. And we have 5 possible interactions. And then we rotate and we compare mass to charge, temperature, time, space, and there'll be 5 sets of interactions. So we can chart it out by comparing taking one against all the others and then the other against all the others. And how many would that be? That would be,
How about you take all 5 and then take all 44 derangement sequences you can make from 5 things and put those as the symbols in those 44 sequences.
yeah, that would be it.
Right, that's us. I was like, well, it's mapped right over there.
And then inside the atom, it just picks from a list of 44 what the legal interactions are.
Inside the atom, it's doing all 44, and when you engage with the atom, it just depends on where you come into it and which one you're seeing. Right? But if you came in this way, you'd see that one and that one. It's the same thing with the mass boundary. So the mass boundary is not,
Relativity is built into the system.
or the mass of the electron, the mass of the proton, and the mass of the neutron are not 3 uniquely identifiable aspects of things in reality. They're 3 bound together things.
I'm done. That's the end of the insight. Other than I want to say this doesn't seem as hard as it did
It's
yesterday.
seeming a little easier. That's good news.
Yes.
That's good. That's what we want. Okay, so we have a physics model. We're claiming maps to mathematics and all of number theory, meaning the structure of our model. I didn't point this out before because I've talked about it so many times it's hard to remember what I've said. But the structure of our model is very unique. Inside, we have bounds that are maintaining a logic that's different than the things outside. Right? The things are being put together differently outside than they're being put together on the inside, despite having all of them being related to each other. What do I mean? Inside, the logic is octonian. It's a different type of system that obeys a different set of rules, different symmetries in the rules. So it has plus and minus rules and divide and multiply and all that work closed in the system, right? But it's an 8-dimensional logic, okay? This is 8-dimensional. Now we have quaternions. And these are 4-dimensional. And what quaternions are a 4-dimensional logical system that have a meaning for plus and minus and divide and multiply and so on, right? But they cohere. They're closed. So you only need them to continue doing all those operations, but it's in 4 dimensions. And then we have the complex math, and it's in 2D. This is the regular x and I directions, right? Imaginary and real directions. And then you can intersect. The quaternions are defined as the intersection of 2 complex. 2 circles come together to make the quaternion connection, okay? So that intersection is 1-dimensional. Take a circle and a circle, intersect them, and then it'll draw the line of where they're touching. Okay? It's just a line. So the 1D that we think of as the real is really just mapping a slice through the intersection of what has to be from these. Follow me? Okay, but this is in our geometry. So this is the hyperbolic figure 8 knot. Down here is doing this. It's maintained its pieces. All of its pieces break apart and twist together and close under the octonian logical balance. And the exterior projection is split. Interior, remember what we call a double cover. So we make the minimal form, but we make it twice so that we can keep it stabilized. It's a double cover. The exterior then, since we're doubling up on the inside, becomes split. It's divided. So something can go around and express itself out that way, and then twist around and express itself out that way, and then come back that way. But it's that one or this one. It's being split in itself. Okay. The quaternion is the split of the octonian division, but it's been rotated also. So there's a symmetry exchange that's different. But other than that, it's a whole set. It's a set that just reduces in form. So this is exterior. This is outside. And this is the interior, the smallest circle-on-circle construction, the logic of the circle versus circle of the interior bound of the exterior projection of our minimal geometry. It's a big sentence, but that was intentional. Okay, so this is real math in our form. It's telling us something real about what's going on the inside. But this is the mirrored action of this. It's just splitting apart. Look, it's just 2D and 4D. It comes from this, but then put together in a different way. We're getting all of the geometric forms from our one geometry. This is a really big deal. Is it kind of making sense of what I'm saying here? We're not just getting where we have math that works coherently in 1D. or in 2D, like in a complex plane, we're getting a geometric system that justifies the existence of logical balances in all of these and only these. There can't be a next one. Why? We quantized. We're on the inside. We limited. We're at the total inside there. You can't go more than the inside. Okay.
Do you think it makes sense to think of it as the correspondence between the 2D to 4D, 4D to 8D is that's how we transition state to state. So to go, if you lived in the quaternion 4D dimension, what we're describing there is a trade-off of, because if you go complex and complex, the transition between those states is represented four-dimensionally, because you're having a transition between those two. So if you live in the quaternion world, the 4D actually is connected to the 8D octonion because that's how you transition in time between the two states.
Yeah, because one time around and then the next time around.
Right.
All of this is just because we're under Mobius construction, right? When I say Mobius construction, I would say there's a balance somewhere that goes around as a circle, and as you go around once, you've returned back to where you started in one way. So you're exactly back where you started, but you're turned around. You might have started out this way, and now when you go around, you're this way. So you're in the same position, but you're backwards from how you were the first time. So you have to go around twice to get back to how you started. Well, this now, put it on our struck picture where we have two circles that are chirally bound. They're both Mobius circles, okay? So this is the construction we're talking about. So this is a fun thing, a window to open, but let me open another entirely different window. Chemistry. If we get the model of physics right, meaning if we have a model of geometry whose internal characteristics, all of the properties you can measure of the geometry, like circle has pi measurable in it, right, and so on. If all the characteristics that are uniquely measurable in your geometry match all your characteristics of physics, then what should follow? You should be able to use your geometry to naturally, easily build chemistry. You should be able to go up from there. Because we currently believe the fundamental building blocks of chemistry, of all the elements in the periodic table of elements, right, are just the same structure of physics. But then put another way, when we look at the periodic table of elements, start at hydrogen, and way over on the other side we got helium, the first noble gas. It's arguable whether you could put it right next to here or there, but this is the standard way, we'll go with it. All right, when we look at that structure, I want you to imagine, well, before we go there, let's look at what the form, everyone here has seen the periodic table of elements before? Yeah, everybody? What's next? What's the next row look like on this? We got one down here, and one down here, and
Two more to the right, probably.
well, there's 6 more. 1, 2, 3, 4, 5, 6. And there's a gap. You know, I got to redraw this because I need the gap to be bigger. Let's put helium over here, or hydrogen over here, and say that. So we have a row on top that I want you to think of as giving us the template of our geometry. Okay? Both our hydrogen and our helium together, both of them at the top, are telling you 2 different scaled expressions of the same geometry. 1 time around the circle, what does it look like? This one. 2 times around the circle, the same circle, get to this one. Okay, so 2 different expressions, the same geometry. And I want you to think of those 2 expressions as the base template of division in our form. So the geometry is being always made by these. Okay? Now, next, I think I should say before I fill these in, no, I'll fill them in. We got 2 rows of 8. So we have another whole row here, and this row has 8. This row has these 2. The next row has how many? There's another row here. And, yes. And then what?
Then 16, right?
Nope.
32?
18.
18?
18, and then
Another 8.
another 18, and then 32, and then 32. So let's make it clear, because it wasn't clear to me when I started looking at the periodic table of elements what the picture was representing. Because a lot of times the picture is so big, they don't want to stretch it way out. So they take the last 32 rows and they chunk them out, take part of them out to shorten the picture. But what they mean is if we made a bigger poster to show you the whole picture, it's just gap, 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 right? It's just 18, 8, 18, 18, 32, 32. Sorry, 8, 8, 18, 18, 32, 32. Now, why in chemistry, and this goes all the way down here, right? It's a square form. All these are filled out, but this only comes to here, and the 18 row comes to part of it, and then it dips down more, right? Okay, so I don't want to draw them all in. Why, in your memory, in chemistry, do they tell you it's 8 and 8 and 18 and 18 and 32 and 32? Why is
It's
that?
the outer shells.
Okay, but why does it have that? Why is that the structure? We tell a story about how many electrons the next shell allows.
Right, that's what it's about.
And the reason? We don't offer. We don't have a reason. Look,
Well, I guess we're saying
nobody
that
knows why this is the structure that best represents the modular, repetitive features that show up in all the allowed atoms in the periodic table of elements. We don't have a clear picture or even a claim for why it's this form. What we're doing with the periodic table of elements is pointing out that we found these symmetries between the atoms, right? That they have a period, it's like plus one more of a certain trait, and that's why we're putting these next to each other. Okay. In our structure, we have, starting again from the beginning, I'm going to put time at the top. And the Planck time has a rotation amount. We put rotation 0. And it has a derange amount. And the derangements for the Planck time are 44. Right? All of them. The time is doing the full derangement sequence, and everything else is lower resolution. Now, we have space. And it has a different rotation, rotation 1, and it has a different derangement amount, and that's equal to 35. Okay, cool. Let me list the other ones out just real quick again. Charge, mass, and temperature. 2, 3, and rotation 4. And derangements of 2, 18. The derangements of mass is 8, and the derangements of temperature is 32. So we're saying we have a structure that breaks apart on the time boundary into 44 pieces, into space boundary into 35, on the charge boundary 18, mass 8, and temperature 32. If this is our base modular form here, this hydrogen and helium, but it's a Mobius form, so it has 2 expressions and you can't go lower than that, then we're saying that form, this whole collection here, comes in these numbers of broken up pieces on different scales. Which one's the biggest scale of the exterior ones? Time and space are the interior ones.
So we won't see.
So we have charge, mass, and temperature outside, right? Mass, and in this case, I'm thinking of inverse temperature when we're talking about making circles instead of temperature, but if I want to make a circle, like say I have a piece of metal, I want to bend it into a circle. A big circle would be far easier to bend it into than a little circle, right? Make a tight little spring. So it takes more energy to bend into a small circle than into a big circle. The big circles will be the mass boundary, biggest scale, because it's that scale of 10 to the negative 8. Which means if we have our base modular form, it's a system that's breaking apart into the hyperbolic figure 8 knot on the inside and the n hypersphere on the outside. And the n hypersphere on the outside is a thing that has 8 big pieces, 18 medium pieces, and 32 little pieces. Pieces meaning the medium itself is being routinely broken up into those partitions chunks, right? I mean, literally pieces. So those are available loops in the partition symmetry of our base modular form. Follow me? They are created by. If this exists and that exists, then those loops are there everywhere. Which means our base structure is a partitioned structure that can support more energy than the base it took to make this in lumps equal to the loops that are already in it. You can say add another loop in that one. When you go around, this time go twice in that one. Or go counterclockwise. So you can add a loop or a counterclockwise loop in every one of the existing partition structures of the minimal modular form. Follow me? When you do, If you start with the easiest ones, the biggest loops, then you'll start in the mass boundary and you'll fill up one more loop in the mass boundary, 2 more loops in the mass boundary, 3 more loops in the mass boundary, and so on, or counterclockwise. 8 counterclockwise possible options because there's exactly 8 derangements in the mass boundary. The next scaled one is the charge boundary. So if you fill all those up, you now have a thing, instead of having a helium, you have a thing that has 8 extra loops in the mass boundary. Or you have a thing that has 8 extra loops negatively in the mass boundary, counterclockwise. Okay? You're absorbing more and more. Next, we have to go down to the charge boundary and loop it up. But the charge boundary has 18 partitions. So in order to fill it up, it takes 18, which is why the periodic table of elements on the next 2 rows is 18 long. And then, of course, once you fill that up, you go to even smaller circles, takes even more energy, and you start filling up the 32 and 32 clockwise and counterclockwise loops already persistently there in your base modular form. And once you've filled that last one up, and you get to the 118th one, you're done. You have filled up maximally, you've wound up your base modular form full. All of its things are as much as you can't do anymore, right? It's taking as much as it can and still being the base modular form. Can't do anything else. So this is either the first black hole or the next push to add more into it is then the first black hole. But I think this is the first black hole. Okay? So the exciting thing here is it's a little bit hand wavy because I didn't show you all the numbers and everything. I'm trying to just get you to the overall argument here. We have a structure that's partitioning exactly into the number of loops that the periodic table says are available to the forms of reality. It's really interesting. And if we take this base modular form and all the rest of these are just looping again in the base modular form, suddenly it makes sense why all the things of reality, all the atoms in existence, all obey the same laws of physics, right? Because they all literally obey the same modular form exchange that's making them. It doesn't become different form as you go more richer, it becomes a more wound up form, right? Okay, that was kind of a big mystery. Why do we have all these atoms? We can put them all on the same chart. They all obey the same set of rules. Why are they even there? We have questions, all of those questions we now have a answer to. Is it right? Doesn't matter. It's inspiring us to continue asking these questions and figure things out, right? Okay. The insight here is that not only do we believe that we're getting close to the right story in the physics, we have details to fine-tune and argue over what's the best representation when we don't have enough significant digits. But by looking in this new way at the data of the constants of nature, of our measurements that we've made in science, using CERN and all of our best tools, we found one simple pattern that allows us to interpret that data. And when we interpret that data, it forces us to the simplest possible modular form, defined as the simplest manifold on the inside, double cover of the simplest possible 3 manifold, the Giesecke constant, or its double cover, the hyperbolic figure 8 knot. And externally, this most beautiful counterbalanced form in all of geometry called the N-hypersphere of maximal volume. This story is incredibly rich and beautiful, but it's empowering us already to make sense of the next level, of why reality is structured with these options only. It's already given us another step of insight. So our goal here is to continue following this chain of insight to get richer and richer understanding of all the exchanges structurally forming the rules of reality and the relationships that make sense of everything we've known so far, so that we can now tap into the things we don't know so far. And with that, I end for now, and anybody that's interested in joining us next times, let us know. All right, thanks everybody.